So the last part of this chapter involves talking about electric fields and electric potential. You should already have an idea of what an electric field is, since we've talked about gravitational fields. Um, and so essentially, an electric field is, again, an energetic aura that surrounds electric charges. Specifically, it's an aura that surrounds electric charges that is only felt by other electric charges. Um, so, uh, just like any object with mass will interact with a gravitational field, any object with charge will interact with an electric field. So, a proton, an electron, a positron, these will all interact with an electric field, regardless of the source of the electric field. But a neutron won't interact with an electric field because it doesn't have charge. It has no way of essentially communicating with that field. Just like a photon cannot interact with a gravitational field because it has no mass. It also has no charge, so a photon can't interact with a gravitational field either. Keep in mind I said photon there, not proton. And so yeah, at the bottom of this slide you see a few different images, and these are images of those electric fields, right? So we see an electric field kind of being emitted. You can think of it as being emitted by that proton or that positive charge. The image B is the electric field created by both a positive and a negative charge nearby. And image C is an electric field created by some sort of parallel plate capacitor. Basically, it's two plates that are facing each other. One side's positive, one side's negative. So it creates this straight moving electric field. The electric field essentially describes the strength and direction of the electric force, right? Based on essentially its direction and the density of those lines in a certain region. So the more lines in a region, the stronger the electric field. So if you look around this positive charge here, right, we see that if I drew a circle here, say, there's a few lines moving through that region. Now if I take that same size circle and move it over here, we see a lot less, right? Just a single line moving through that region. So we can see that the electric field strength is stronger here, weaker here, stronger, intermediate here, right? The unit for, and the electric field follows the inverse square law, just like the electric force, right? Just like the Coulomb law. In fact, you can see an equation for an electric field around a point charge. So this is an example of a point charge. Here. So this is this equation. And notice that it's pretty much Coulomb's law, but it's just missing a charge, right? So an electric field, you only need one charge to exist for there to be an electric field. But for there to be an electric force, you need two charges. So that's where that second Q comes in the equation, and that would give us a force. You might, again, remember that the acceleration of gravity, which is a representation of the gravitational field, had an analogous equation, which was capital G, that constant, times the mass we're looking at, over r squared. And the last thing here is that the unit of an electric field is force per unit charge. Again, if we, so force per unit charge. So newtons per coulomb. Now, with gravity, as we said before, there's one type of mass, positive mass, and so gravitational field lines always point towards that mass, the source mass. Electric field lines, however, have two sources. There's a positive and a negative. So essentially, I think about it like this, right? Positive mass, there's only positive mass, always follows the direction of the gravitational lines, the gravitational field lines. So if I let go of a ball, we wouldn't expect it to go away from the Earth in the opposite direction. So similarly, positive charge follows electric field lines. So we know positive charges move away from other positives, right? They repel. So the electric field lines point away from positives and towards negatives. Again, if I put a positive charge near this if I put the positive charge near this negative charge, it'll move towards it. So protons or positive charges follow the direction of the electric field, whereas negative charges, like electrons, go in the opposite direction. So if I put a positive charge here, it'll move up. If I put a negative charge, it'll move down. If I put a positive charge here, it'll move down, and a negative would move up. We can use this animation here to get as an example of the strength of the electric field. So we see a positive at the center, and so our electric field lines are going to point away from that positive. So if I put one right next to the charge, we see that it's quite long, right? It's very strong. If you look at the graph, we see that we have a distance from the central charge versus the strength of the electric field. And right here we have a strong one. Let's get some more so you can actually see that. So if I go a little bit farther away, it weakens a bit more. And as I get farther away, we see that the strength of that electric field vector drops very quickly. And it drops really quickly because of that r squared, right? If it wasn't a squared r, it would drop slower. Yeah, and then of course if we switch the charge in the center, again our electric field is strongest the closer we are, and weaker as you move farther out. All right, so that was electric field, right? Very much analogous to an gravitational field. But with electricity, there's one extra thing to introduce that we didn't really use when it came to gravity, and that's called an electric potential. But real quick, before we get to electric potential, let's talk about electric potential energy. These are two different things. So we know that the higher an object is relative to the Earth, the higher its gravitational potential. So like in this image, the higher we lift up this block, when we cut the string, the block falls and the potential energy turns into kinetic. The higher it is, the more kinetic it gains. We have a similar process with charges. So the farther away we load up a positive from a large negative charge, the higher the potential energy between it. And when we cut that line, the positive gets pulled towards that negative. And the higher the potential, the higher the kinetic the positive charge will have before colliding. Similarly, if we have two like charges near each other, it acts more like a spring. So as I push this small positive charge towards this large positive charge, I have to do work to get it there. And it's just like the work I would have to do to load a spring. And then as soon as I let go of that spring, the spring shoots outward, just like this positive charge would shoot out, repel, once I let it go. Alright, so now we want to talk about something called electric potential. This is not electric potential energy. They're very closely related, and unfortunately they were given names that are way too similar. So again, there's electric potential energy measured in joules. It's an energy just like everything else, all the other energies we've discussed. Electric potential is a new concept. Another word for it is voltage. So that you've heard of before. Now, essentially, electric potential refers to the potential energy per charge in an object. So if I have an object with 10 coulombs of charge and 10 joules of potential energy, then I'd have an electric potential of 1 volt. But if I had, let's say, the same 10 coulombs, but now I gave them 20 joules of charge, they'd have 2 volts, right? There's 2 joules per, 10 coulombs with 20 joules of charge. Yeah, it would be 2 joules per coulomb. In other words, 2 volts. Yeah, basically this equation. So for now, think of electric potential as just that. It's the amount of energy per charge, as opposed to just the total amount of energy. When we look at circuits in the next chapter, we'll have a different way to think of electric potential or voltage that I think is a lot more useful. So yeah, that's it for chapter 22. I'll see you guys at chapter 23.